every element has electron and a proton, and then the basic one is the hydrogen. The next one up is helium, which has 2 protons and 2 electrons, and then it goes into lithium and so on. The smallest part of the electrical charge is the negative one, and it's physically smaller, and the larger particle is a proton, which is in the nucleus. The nucleus of an atom has neutrons, which is kind of like they take a proton and an electron and combine them together. The electrical weight is, they don't affect what we're doing, but they are make for heavier atoms. And so the main thing we're worried about is the electron, and so an atom that hasn't been messed with has the same number of electrons as it does protons. And we'll talk about the electrical characteristics of certain elements with regard to how many electrons they have in their outer shell, and that will vary. And we'll take a look at that in just a second. So when the outer shell of an electron is filled, it doesn't want to combine to make compounds or molecules. So water is a molecule of water is 2 hydrogens and 1 oxygen, and once that combines, they're basically relatively stable until you put extra pressure on it. So what happens is the outer shell of oxygen wants 2 electrons, and the hydrogen wants to get 1 more electron, so it'll have 2 in its shell. So what happens is the hydrogen shares its electron with one of the outer shell oxygen, and so the hydrogen, there'll be 2 hydrogens with 1 oxygen. So the oxygen now says, "Oh, I have 8 electrons in my outer shell, so I'm relatively stable." And the hydrogen says, "Now I have 2 electrons," and so there's a bond there, and they stay together until you put some external force on it, heat, or if you stick a piece of iron into water. The iron, which also has incomplete electrons in its outer shell, it wants a whole bunch of electrons. It has enough force now, it will draw the oxygen away from the water and form rust, ferric oxide. But what happens is you put that iron in there and you'll see little bubbles on the nail, and that will be the hydrogen. If you take water and you put electrodes in it, a negative and a positive, and put some voltage to it, hydrogen bubbles will form on one of the leads and oxygen bubbles will form on the other, and that's how you can separate hydrogen and oxygen from water using electronics or electrical current. And they're doing that in some countries to make for hydrogen powered cars. They have basically hydrogen generators, and they're just taking water and using a negative and a positive lead to separate the gases, and then they separate the hydrogen, compress it, and you can recharge your car at home, hopefully. That's the plan. We'll take a look at some of these atom assemblies and specific combinations here in just a moment. So here we have hydrogen, again, 1 electron, 1 proton, and this basically orbits around this nucleus, and this wants to have 2 electrons, so that's why hydrogen forms so many compounds. Again, we talked about water, H2SO4, hydrosulfuric acid, which is in your car battery. Hydrogen wants to make recombine with something. That's what the Hindenburg was all about. It was a big chemical process. It didn't explode. It was a slow burn in the sky because it was a slow chemical process. So the electrons are in orbital rings, and they're power levels. And the one we're most concerned about is the outer level. And we'll see here in a second that these rings, here we have a KLMN. Well, you start talking about uranium or some of those, there's a whole bunch of these strings out here. When you start talking about 100 and some odd electrons moving around 100 and some odd protons. Here we see a semiconductor, and this is carbon, which is element 6. Well, the 6 means on the chart, have the complete list. So we start off with hydrogen is 1, helium is 2. So helium would have 2 electrons, and it doesn't form compounds. Then lithium would have 2 in here and 1 in this in the L shell. Is that the lithium? Well, we're going to go up to carbon is number 6 element. And so it has 4, and that's called a semiconductor. So it either wants to give up these 4 in some way or gain 4 more in combination. Now silicone, what will happen is silicone will have 4 more silicones around it, and so it forms a a silicon, it's almost like a doily. It's called lattice structure. And so essentially it can form a stable, relatively stable factor and so on. And then we introduce things with extra electrons or lack of electrons to get N material or p-type doped material in the semiconductors. This one is copper, which copper is the 29th element. It has 29 protons and 29 electrons. Well, here we see there's 2 in the inner shell, the K, 8 in the L, 18 in the M shell, and then it wants to have 8 in this outer N shell, but it only has 1. And so, again, the distance from the nucleus, the farther out this electron gets, the less force it takes to put it in motion. We talked yesterday that the voltage is also called E, the symbol is E or V, and the E stands for EMF, electromotive force. So there's a force that comes along that pulls that electron here and pushes it onto the next atom. So essentially, an electron can come along from another copper atom onto this one and jump, or it's kind of like daisy chain its way along. So when we put a pressure across a wire, you're pushing the electrons from one side of the wire to the other. And you start thinking about, at the speed of light, the electromagnetic dam up at Grand Coulee Dam, those electrons are going from here to Grand Coulee 60 times a second. Conductors, which usually have their outer shell is not filled. Here we have 3 examples: silver, copper, and aluminum. And a better conductor than silver. Silver is really good, but gold is better, and platinum silver is the best. When that outer shell, they call it the valence shell, the outer shell around the atom is complete, meaning if it wants to, like helium, it has to. If it has 8 in it, then that's in the outer shell, then it's complete, meaning it doesn't want to make compounds, and it takes a lot of pressure, external pressure, to break that down. So you can't take an insulator and make it conduct. A good example of that is gas. In neon lights, fluorescent lights, gas typically is an insulator. But you put enough force across it, and it will break down and conduct. And when it does, it gives off photons of energy. That's how you get your photons in your torpedo tubes. It gives off energy. In this case, the energy in fluorescent lights is not in our light spectrum. So what they do is they coat the tube. When you break the tube, there's a white powder in there. But the photons of energy from the gas ionizing, or basically conducting, breaking it down and making it conduct, gives off photons of energy. The energy that keeps that electron in proximity of the nucleus, when that electron moves, it gives off energy. It's a photon of energy that hits that phosphorus and makes it glow. So it's a phosphorus that's glowing, but it's a fluorescent gas that ionizes. Neon, when you turn on your range, your stove, a little light comes on, so you got power someplace. That's a little neon bulb. And that neon bulb, it takes about 60 or 70 volts for it to break down. Well, you have 120 volts coming out of here. So what they do is they put a little resistor in there that drops the extra voltage, and so that little neon bulb will light. I have an extension cord, which is nice, that has a little neon bulb in the female end of it. So when you crawl underneath the house and you disconnect your trouble light, that extension cord still has a little NE2 light, so you can crawl around there in the dark and grab the end of the extension cord so you can plug it back in. But essentially all it is, if you look at it, there's a little neon bulb that they call an NE2 and a little resistor to drop the extra voltage and keep that the current through there at a minimum. You don't want to fry that little thing. So yes, there are insulators, but what happens is an insulator says it takes a lot of energy or a lot of external force to break down that bond between the neutron and the electron to get that electron in motion. That glass can probably take 20, 30, 40, 100,000 volts, but eventually you keep getting the potential across it, you will punch a hole through the glass and get it to conduct. It just takes more potential. So insulators basically take a lot of force to get the electron in motion. A conductor takes very little pressure to get that electron in motion. Here we have 3 examples of semiconductors. Again, the most common one is carbon. Your pencil, they call that a lead pencil. It's not actually lead, it's graphite, which graphite is a form of carbon. So if you took your number 2 lead pencil and you draw a real heavy line on a piece of paper and you take your ohm meter, well, we can do this later on, is you put your ohm meter across that, it has resistance. And so the voltage in the ohm meter, when you put it on ohms, there's voltage on those leads, and you put that voltage across the graphite line, you force electrons to conduct, and you'll put current through that graphite line, and you'll be able to measure the resistance. Basically, that's what a volume control. So if you took those two leads and you bring them together on that carbon line or that graphite line, they will the resistance will go down, just like a potentiometer is, like a volume control. You'll have less and less resistance as you get those, because there's less carbon between the two. So when they're equal, then there's a balance there. So if a copper atom, we take that electron away, now we have more positive charges than we have negative. So if you put a battery across a copper wire, one of those copper atoms is you're taking the electron away from it. You're forcing it, the EMF, you're forcing the electron away. So now that becomes a positive ion, meaning that an ion is an imbalance of charges. And so now the next copper atom says, I have an electron out here, and there's a positive ion. There's enough of attraction, it'll draw that electron over. Now this one's balanced, and this one's a positive ion. So it's kind of like electrons movement. It's kind of like what's that game we have, a chair that nobody sits in? It's kind of like as the electrons going this way, the lack of electrons are going that way, or the absence of electrons. Some texts, that's called conventional current flow. So engineers in some of the textbooks say the holes or the lack of electrons are flowing this way, while the electrons are flowing that way. As technicians, we follow the flow of electrons. Engineering schools follow the whole, and that for some reason right around World War II is when the textbooks separated on that.